Oh. Okay, class. So we will continue on our next lecture. Okay, about the switching loss. Okay. So like I explained, switching loss, right, is a phenomenon when the transistor turn on and off. All right. So if it's used for just normal on and off operation, okay, it doesn't really matter, if you just turn on a light and off a light, for example, okay. But if you are used in a converter that you are turning on and off, okay, at the high frequencies, for example, like, 10 kilohertz, 20 kilohertz, and then this switching loss, okay, will really need to take into account, okay, of your converter system. It even so important until you can actually find it in the data sheet. They actually tell you, if you use this transistor, what is my turn on delay time, what is my rise time, what is my fall time. So that means it's a very important parameter. All right.
Excuse me, sir.
Yes.
Can you please share the screen?
Oh, sorry. You all cannot see, right? Okay. Okay, can you all see now?
Yes, sir. Thank
you. Okay. All right, switching loss again. Now, even in the Simulink MATLAB, right, it's so accurate in the way that you can actually simulate, okay, you see all these delay. It does happen, okay, that is very important, it does happen. There is no ideal transistor in the world, okay, there's always have, like switching delay, okay, turn on resistance to consider. Now, if we look at the switching waveform, we basically can divide it, okay, into 6 different frames. So which is the turn on delay time, rise time, turn on time, turn off delay time, fall time, and the off time. Of course, the off time and on time will not be given in the data sheet because it is depend on your duty cycle switching. All right. But this turn on delay time, rise time, turn off delay time, and fall time are fixed. Okay. It's, like I said, it is stated in the data sheet. So these are some examples where you can actually find this information, okay, in the data sheet. All right, it's all stated. Okay, these are the 2 different transistor. One is IRF 540, one is IRLZ 44. Okay, now let's take an examples. We have a MOSFET, okay, where the VDD is 40 volt. The RDS is 0.28. And the ID is 25 amp. Okay, and the VGS is 10 volt. The IDSS is 250 microamp. IDSS is the leakage current, okay, or the reverse, okay, current. And we have this turn on delay time, okay, the rise time, turn off delay time, okay, and the fall time. So all this information, right, you can actually obtain from the data sheet. Okay. I don't know which one I picked lah. Definitely it's from either one of the data sheet. Okay, it can be obtained from the datasheet. Then, of course, if you really design a real circuit, right, then you decide the voltage, right? So you can base on your real circuit. Now, the switching frequency is 20 kilohertz. All right, and the duty cycle is 60%. So with all this spec here, you should be able to actually calculate the switching losses. So let's go through it. Now, the first part is the turn on delay power loss. All right, so turn on delay power loss is basically this segment. Okay, so you see the yellow color, right, is a VGS. So you see, the moment you already apply voltage 10 watt to the VGS, right, you will see it will take some time before the rise time, right? Before the rise time, so it takes some time. So this is governed by this equation. The power, okay, the turn on delay, which is equals to the VDD, okay, the applied voltage multiply by the IDSS because it's still not yet turned on. Okay, so it's IDSS and then multiply by the turn on delay time multiply by the switching frequency. So with this one, okay, now I didn't put in the value. So what you all need to do is just to make sure that you substitute in all this value. So here, if everything is correct, you should get 5 microwatts. Okay, that means I gave you the equation, I gave you the last answer. Okay, it's up to you to put into the equation, okay, and get the answer. All right, so I don't work out, okay, the answer for your step by step because it's applicable, okay, to different, you know, what we call this MOSFET. So with that one, you should be able, okay, to actually start to calculate, all right, the turn on delay power loss. Okay, so at this point, any questions?
Excuse me, sir.
Yes?
Could you repeat what is IDSS?
IDSS. Okay, IDSS is the reverse leakage current. You see, IDSS, when you look at the any MOSFET, right? This is the D, this is the S, and this is the G. So when you apply voltage across of it, when the G is 0 volt, right? Theoretically, it should turn off, right? But it does have a very small current that is leakage, okay, leak through it, in other words, okay, at 250 microamp, which is so small that it's almost considered as turn off. So this is IDSS. You can find this IDSS in the data sheet, okay? Somewhere around, okay, if you find the data sheet, okay, let's say, okay, this one. Okay. You see, there is IDSS here. The IDSS, drain to source leakage current. All right. So it's between the range of 25, okay, to 250 microampere. They only give you the max. There's no minimum, no typical. Okay. So it depends on the condition. All right. So in this condition, when you apply your VDS is 100 watt, but your VGS 0 watt, you will have like 225 microamp as a leakage current. Okay, it's so small that it considers it is in the off condition. All right, am I answering your question?
Perfect, sir. Thank you.
Thank you. So don't worry, like I said, all this information is inside the data sheet. The only important is that you must know where to find this information and put it into the equation in order to calculate it correctly. So please at least go home and do one round yourself. And this is going to come out, okay, in the exam as well. Okay, so that is the turn on. You see, just the turn on delay itself, right? It already will give you some power loss. Okay, now 5 microwatts. Now, next one is the rise time. So the rise time, okay, is the time it takes to rise from 0, okay, to the top, right? For the current. Or the voltage, as we know that, right? Current go up, voltage go down. So it's always, okay, complement to each other. So in this case, in order to calculate the rise time, all right, now this rise time, right, you will see different textbook may give you a little bit different of equation, simply because the rise time is not really a fixed triangle, because this triangle, right, it depends on your rise time, right? If your rise time is shorter, right, the angle will be steeper. So different textbook, they will give you different, a bit different, not say totally different. Okay, so I choose to use this equation much more general that you can approximate most of the rise time. So rise time is, now you know that rise time is the process of turning on. So you need to multiply VDD, multiply by your IDS. You see, V multiplied by I is what? Is power, right? So power loss, you always see the V and I. Even in the previous one, okay, you see, it's the V and I. This is the power. But the power, okay, happen at a very short time. Multiply the time, multiply by the frequency. This is how the equation come by lah. And then from here is the same. It's the power, but the rise time, okay, and multiply by the frequencies. Okay, multiply by the frequencies and divide by 6. Now, like I said, you will see some equation, they will divide it by 2. They take it as a perfect triangle. Triangle. That's why you divide by 2. Okay, so there is, so far I encounter, there are so many different, some they divide by 4. Okay, and then like I said, sorry. Oh, IDS is the turn on current. You see, IDSS. Okay, IDSS is the current. So IDS it is on ID. Yes. When you turn on, right, how much current flow through? Okay, how much current flow through? Okay, so it should be a S there lah. So be careful on this. Okay. Now, after you calculate this, right, you should see there are approximately, like I say, a general equation from textbook is used. All right. Unless you can confirm the exact pattern of this, then you can derive the accurate equation. Okay. Because it is not a pure triangular, but if you confirm it is a pure triangular, right, you just get the voltage and the current divided by 2, but it's not, because you see, even I use MATLAB to simulate, you can see the rise time, right? There is a small little curve here. You see, there is a small little curve here. Okay, even you see the one that go down, they have some curve, right? So it's not a pure triangle. Yes. You get 0.2. 1/6.
So I also get 0.2 instead of 0.25.
Oh, okay, then it's my mistake. Wait, let me confirm. You all use this equation. All of you get 0.2. Right?
Yeah.
Confirm. Okay, good. This one need to be confirmed. Then it is 0.2 lah. Okay, I need to confirm your IDS is 25, right? Your VDD is 40, right?
Yes.
And the turn on rise time 60 nano?
Yes.
Ready, Okay, good. Then it's 0.25. Okay, no, 0.2, sorry. Okay, this most probably is my previous note answer. Okay, because I changed data sheet already. All right, so now we already have the rise time. You see, every time it turned on, right, you lost 0.2 watt. Okay, so you know that is the power loss happen, okay, in the transistor. Now we move on. Okay, now move on is the conduction time. Okay, conduction time means that it's the time that when the power is on because they already turned on, right? So conduction time is pretty much easier to calculate because we know that it's a rectangular already lah. Okay, so there is no voltage, but we have current. Turn on already, current full through. So we use a I square R. You see, it's all power equation, I square R. In power electronics, right, we're dealing with a lot of power, so it's I square R. Then we multiply by the turn on time and multiply by the frequency. Now, what is the turn on time? Now, turn on time, remember, is a duty cycle, right? So the duty cycle, this turn on time, duty cycle, okay, D 60%, right? A duty cycle, wait, 60% divided by the frequency. And then you need to minus, okay, this rise time. Okay, we need to take account of this rise time and also minus the turn on delay time here. We need to remove this one. Okay, we need to turn. Okay, so now you calculate what you get. My answer is 10.47. Let me know if you have a different answer.
Excuse me, sir.
Yes.
Could you please go back to the given data? I mean the question. Yeah, okay, thank you.
Yeah, you should be able to see it on the slide, right? I'll upload it. 60% of duty cycles. Okay, that's all you need to know. And of course, the rise time and the turn on time. Okay, let's see what you all get.
Excuse me, sir. What's the small letter D on the time on formula?
Small letter. This one. This
No,
one is.
the D over switching frequency.
This is a duty cycle. Here. 60%. This is the duty cycle. So you have to put 0.6 lah. Okay, this is the duty cycle. Answer? Anyone get other than 10.47? I said, please do it now, so you won't get it wrong during your exam. To be very honest lah, in the past, right, most students make mistakes in the middle of the, you see, this question is very critical because there are so many turn on time, right? If one part wrong, the last one is so wrong already. So you cannot afford to make any mistake. Yes. IDS cannot calculate. It's given. It's in the data sheet lah. Yes. Yes, it's given. Okay. Yeah, it's in the data set. You see the IDSS, the IDS, it is all given here. You see, even you see in the data sheet first page, right? It will actually show you this the maximum voltage, the maximum current you can apply to the transistor, and this is the RDS turn on resistance. Of course, in real design, the ID is not the maximum, right? Because you know you may have some circuit, then the ID may be like 16 or 35, I don't know, right? You have to define yourself lah. So these informations, okay, they are actually available, okay, in datasheet. Okay, right? Okay, I think most of you will get the same answer being said. The answer here is correct, so I move on. Okay, then after we know the turn on time, that means when you turn on, right, there are power losses at the transistor already due to the turn on resistor, right? And then it dissipates in the form of heat. So this 10.47 watt, right, will dissipate in the form of heat. Okay, now we go on to the next step will be the turn off delay, okay, power loss. Means that you already turn off, you see the yellow color, but your transistor remain turned on for a very short moment of time. Okay, so this turn off delay is pretty straightforward. Okay, so again, like you see, it's a power equation. It's always a power equation, all right, multiply, okay, I square R, the power equation, multiply by the delay of time, multiply by the frequencies. Okay. So if everything is correct, you should get this 0.025. 245, okay lah. Yeah. And then now we move on, okay, to again the fall time. Now fall time and the rise time is the same. Okay, like I say, I use a general textbook equation. Okay, unless you can confirm it is a pure triangle lah, then you divide it by 2. Okay, or else because it is not a triangle. Okay, in actuals, so you can see that it's actually the same equation divided by sec. The difference is that you change this to the fall time. So it's still the same, the voltage, current as power, multiply by fall time, multiply by switching frequency, and divided by 6. So if everything okay, you should get like 0.083 watts of the losses. All right. So after that, the last part, okay. Now the last part is the off time power loss. Okay, off time power loss. Okay, again, you will see that it's the opposite of the on time. So off time is no longer ID. Okay, it's IDSS already. This is the off time current, which is very low. Multiply by your voltage, multiply by your off time, and multiply by your frequencies. Okay, and the off time here is 1 minus D. D is your duty cycle, right? So we know that 60% of duty cycle means that your switching pulse is 60% on, 40% off, 60% on, 40% off. So this is 60%. So, and we know that, okay, the off time here will be 40%. So this is how we get the 1 minus D. You will get 0.4 here. Divided by, okay, your switching frequencies minus your fall time and minus your turn off delay time. So you should get 3.981 milliwatt. This is a very, very small power loss. So many zero, right? Of course, you can round it to 4 lah. 4 milliwatt also can. It's so close already to 4. Same, right? Correct, Okay, good. I need some verifications. Okay. So now, if you want to calculate the total switching power loss, is to basically add all them together. Okay, the power loss of the turn on delay, power loss on the rise time, power loss on time, power loss turn off delay time, power loss of the fall time, and the off time. You just add all them together. Okay, so once you add all them together, you will have a total of 10.83 watt of power losses. Okay, power losses. So you are running a 1000 watt, okay, supply with 10.83 power loss. So meaning that it is able, this transistor, right, is able to deliver to the load is 989.2. So you will have the power efficiency of 98.9%. Okay, 98.9%. So meaning that from all these power losses, right, you can see which part contribute to the largest. It's actually the turn on time. This one contribute, if I'm not mistaken, I think is 10.4. Contribute the most. The rest are very little. But still, that's why selecting of a transistor, okay, with a suitable RDS is important. Because this loss is directly, okay, caused by the turn on resistance. All right. So you change the transistor, right? You can immediately change, okay, the power loss. And also remember that the switching loss is caused by switching. So switching is switch by frequency. If you look at the equation carefully, right, every equation, right, will have multiply of frequency. You see, multiply of frequency, multiply of frequency, multiply of frequency here. All got multiply of frequency. So meaning that the higher the switching, the higher the power loss. Okay, so you don't say, wow, go maximum 1 mega, jante. No. Okay, so there is a balance point lah. Okay, there is a balance point lah. Too low sometimes cannot work properly. Okay, too high is a bit overkill and you cause more switching losses. All right, that's why this switching thing, right, also not just happen in power electronic, it happen in your computer CPU. Now our CPU getting so hot as when our frequency increase, right? 1 giga, 2 giga, or play game, right? Oh, you shoot up to 2 giga, 3 giga, your CPU become hotter. Okay, simply because when you look into the basic fundamental of the CPU, right, arithmetic unit, they are all made up of transistor. So the transistor is switching at that kind of speed. Of course, it will have more power loss, but power loss is not an issue for like CPU, right? Because we have almost like, okay lah, you just increase the power supply lah. What they want is the speed of processing. Okay, of course, nowadays you will notice that they can no longer increase the speed already. Because it's too hot. It's already too hot. Okay, the switching speed already hit the critical limit that the silicon material, okay, cannot handle it anymore. That's why for the CPU, they venture into like multi-core architecture, using 2 core instead of just keep on increasing. It's just like car engine, the RPM, you know, it's not infinite one, you know, you cannot keep on increase the RPM. Okay, the engine will heat up, okay, and the torque will reduce. Okay, so these are things to consider lah. Okay. So I believe you all should know how to calculate this already, all right? Efficiency is basically the total power applied to the switching, which is 40/35 lah, which is P equals to IV lah, okay, or ID VDD lah. Okay, so this is the total power applied. Okay, so the switching will give you some losses, and you know that, oh, okay, you only get 989.2 watt when you apply 1000 watt. Okay, the rest of the 10.83 dissipate in the form of heat. I'm talking about just one transistor. Okay, I'm talking about just one transistor. That's why in a CPU, there are millions of transistors inside. Even the losses is very small for each of them, but when you accumulate, right, you can see we need fan, we need cooler, everything. Okay, so that is a fundamental, okay, of this switching loss. And then, like I said lah, please make sure that you get every step correct. Okay, so if you get it wrong in the middle, your total answer will be wrong. Your efficiency will be wrong. All right. So you see, this question can be like that. Easily can be 10 mark here already. Okay. Calculation this part maybe 1 mark or 2 mark. I depend. Okay. 1 mark, 2 mark. Okay. This one usually 1 mark lah. Okay. Let's say 1 mark, 1 mark. But this one got 2 step . So 2 mark lor, 4 mark, 5 lor, 6 lor, 7, 8 lor. Okay, 8 mark there already. Okay, and then this one 9 mark lor, and the efficiency 10 mark. Something like that. I will divide into this form. Okay, now the critical is that if you get the wrong value from data sheet, that's it. Everything wrong. Okay lah, I won't be so cruel lah. I will still give you 1 mark for fun, for your effort to put in to write something wrong for me lah. Okay, so it really depends. If you get the first one correct, second one correct, but this one wrong, definitely all this wrong. Okay, you got 2 mark for sure. Maybe I add another mark for all this wrong you gave me lah. So this is how the marking will be lah. Very critical. Of course, if you do wrong at the last part, okay, you gain most of the mark. Okay, so it's something like that. Okay. Now you may ask me, if I get this wrong, and you get this right, you get this wrong, get this wrong, get this right? So this one, I don't know how many marks. I will give you this mark. I will also give you this mark correct. This one plus this one, because this so wrong already. Something like that. Okay, if it's not in the sequence. Yeah. We will look for typical. If no typical, then it either give you minimum or max, right? Either one. Okay, it's not like VGS, they give you minimum, maximum, no typical. Then we need to get the in between. So
normally you take typical first.
Yes.
Okay, if the typical didn't state, then you take maximum or minimum.
Whoever it give you.
Okay.
Whichever it give you. And usually in the question, sometimes I do state like, okay, we use ID, how many current? How much current? Or I will purposely state, okay, VDD, let's say I state 30 watt instead of 40. Then you have to follow my VDD already, right? Then the rest you have to find from the data sheet. You don't go and follow everything data sheet, but you don't follow my question. So read my question carefully. Things that I can change, okay, is basically the VDD and the ID. Okay, these are the things I can change any number I want. This one I cannot change because data sheets say this one is this one. I cannot change, right? Whatever I cannot change, you will need to find a data sheet. Whatever that it's variable. Like say this transistor not necessarily you apply 40 volt, right? You can apply anything, depend on the data sheet lah, how much you can. Okay, how much you can. Or I can just tell you, say, okay, use the maximum power of this transistor. Now, if I talk about maximum power, maximum power means what? You have to look at the first page already. Look. Maximum wattage is 100. Maximum current is ID. This one multiply, this is the maximum power. Because these two is variables. It tells you that this transistor can withstand up to 100 watt. And usually we don't use up to 100 lah, right? We tell what all this. That's what we apply, right? And then of course this one, it will give you different current. So maximum power means that, okay, we use 100 watt, it will give me 33. And these are the, you know, the information that you need to fit in. The rest like IDSS also, okay, now like you say lah, this one got two value one. Okay, but this one means that it is running at temperature of 150, but usually we will see at temperature of 25.
So it's like the case of VGS now.
Which one? Oh, this one I told before already, when do the modeling. We take the medium, the average lah. On paper, we do it on average, like, okay, no typical, minimum 2, maximum 4, so we get 3. But as we know that 3 also not so ngam lah, because when we do model, we know that it's 3 point. Okay, that one because we can't tell, because it really you need to model only, you know what is the actual. But let's say you don't have model, but you want to quickly know, calculate, take the medium, which is the average between the minimum and the maximum. And you will see that most of them, right, they will give either minimum, typical, or maximum lah. Very, very rare they will give you both. Usually the both one, that's mean they themselves also don't know. They know it's 3 lah, but you know they better put like that so you can play around. Because they put ngam 3, let's say we do design based on 3, then it doesn't work out. Then you complain, then you know. Okay. Okay. So basically, yeah lah, switching one, the most important actually is this 4 lah. Okay, from data sheet lah. The rest, this one I can change. I can tell you I want to run at how many megahertz. Duty cycle is also depend on your design. This one is fixed. Okay, this one is fixed. VGS basically we don't use all right. And IDS and of course the VDD lah. The VDS and the ID it will not increase or decrease at the same time. It's always opposite. Okay, you can see this one. Okay, when the ID increase. Okay, and the VDS okay decrease. That is simply because transistor right? The transistor is here. When you turn off, means that there is a very high resistance here, right? When there is very high resistance, means that the current low at this point, the current near 0. Okay, of course it's not 0, it's 250 microamp and the voltage drop, right? Because you are connecting to a DC source. If this one, let's say, is 10 volt, then you will have a 10 volt here lah. So when turned on, right, this resistor become very, very low in milliohm. Okay, so your current will increase and the voltage drop across here will decrease. Okay, so it won't be increase and decrease at the same time. This current and voltage is always complementary. All right. Okay, so that is about yeah, the switching loss, okay, equation. So every time, right, you will never get a repeated question because there are thousands of data sheets out there. I just go and pick one for this round exam. I also don't know sometimes the answer. Okay, so yeah, just to make sure that you all know how to get the right value lah. Okay. I have written a very simple MATLAB, okay, for you all to play around. Oh yeah, I forget to put the link. Okay, never mind. I'll show you where is it. Again, you go to MATLAB file exchange. And then maybe just type transistor switching loss. Transistor. Oh. Sometimes, so you will see the, you can download this program here. Okay. You can download this program. Okay, and then you can run in MATLAB. Okay. Okay, this program I written, okay, to demonstrate the switching loss graphically, so you can see. But you cannot get the same losses based on the calculation because the switching loss calculation does not, okay, include this turn on delay time and this off time into account. Okay, so these two components I didn't add in. It's not meant for you to, like, what we call this, to use this automatical calculator. So the purpose is, okay, you can see that. So the red color again, okay, is the transistor, right? Turn on current, and the blue color is the voltage, and the yellow, okay, is the what we call the VGS. So from here you will see that this is power. You see the power losses, right? During the turn on and turn off time, you will see two peaks. Okay, so you can see these are the power losses. Okay, the power losses. And then it will have a constant loss, okay, across the time. Okay, across the time, and then it switch off again, you will have another peak. So you can play around with, by changing all this number, okay, then you can see how it affects the switching loss. All right, so this one I still make the frequencies fixed. 1 kilohertz, duty cycle is 0.1 second. Okay, very, very short turn on time. If I'm not mistaken, I'm basically following the data sheet, okay, to do it. So you can see that if I increase the RDS, 0.044, maybe I increase 10. You can see that, right? The turn on time, the turn on power losses increase so much. Okay, it increase. So you can change here. You can see if I put back to 0, it go back. Okay, so this will affect how the power losses. And then again, let's say I increase the turn on delay to 20. Now you can see, okay, it turn on delay. And then maybe the rise time I increase to 60. See what happened. Now you see it increase, right? You can see this portion become bigger. Okay, this portion become bigger. Let's say the fall time also I increase to 50. Okay, you can see, right? So these two peak, okay, will indicate, right, the power losses. All right, the power losses. So it just gives you some idea that, okay, every time when you switch, right, you will actually create these power losses. And you can see that the time here is in nanosecond, very fast switching time. Okay. So you can actually play around with this number and see, where is this power loss, okay, came from lah. Okay, like I said, this is just a demo to let you all see, because in the textbook, right, they only show you this, but they didn't show you the one that at the bottom. Okay, so this is very important. You will have a power loss spike during the on transition and the off transition. And of course, your resistance increase, let's say 0.08, and your power loss, you see, it will increase. Okay, it will increase. And if I increase 9 at 1, you can see it go up. Okay, it will have this. So the what we call the RDS is also one of the factor lah. Okay, that determine the power loss. And let's say if I increase the current, okay, well, I see go over the chart already. And you can see that the power loss, okay, also increase. Okay, the power loss also increase. Okay. So these are just a software for you to play around, to visualize the problem, okay, where no textbook has really show you all. Okay. This one I'm based on this textbook, the one. If you look at my very first slide, okay, I based on this textbook. All right, based on this textbook, okay, for the equations. Okay, so that will be the transistor switching loss. Any questions? Yes. Because of the transition, the voltage and the current multiply, you will have the peak, right? You can see the voltage and the current. The voltage at this point multiply the current, so it will cause a two peak. That is the power loss. Okay, we done switching loss. Now we have to move on to the next part of the transistor. Okay, which is the thermal modeling. Now we know that the result of the switching loss is heat, right? You create heat because of switching. Okay, and then the next part of the transistor is how do we deal with this and how do we model heat, okay, in a transistor. All right, so we will move on to transistor thermal modeling. So the first question is, why transistor need heat sink? So obvious, right? Because it want to dissipate, okay, the heat. And why transistor heat up during operation? Also answer already, right? Because of the switching loss. Okay, the switching cause the power dissipation in the form of heat. And then power dissipation due to RDS, right? The RDS, okay. Of course, there is no RDS 0 ohm lah. If 0 ohm means, no power already, no loss lah. Okay. So that leads to thermal. All right. So now if we look at a simple power dissipation Simulink here, okay. Now we apply 10 volt, okay, 10 volt in this VGS, and then we measure the voltage across the DS. Okay, measure the voltage across. And then we measure the current, which is ID. Okay, and this is VDS. So we multiply them, VDS multiplied by ID, you get the power dissipate across this transistor. All right, we don't multiply the frequency because this is fixed one. We are not turning on and off, right? Fix that. So you can actually see that, oh, during on time, okay, the transistor will actually dissipate like, 0.97, okay, watt, okay, 0.97 watt. So every transistor, when it turn on permanently, let's say, in this case, it will actually dissipate power already, okay, it dissipate power. So again, even without any switching, you just turn it on like that, it will dissipate power. And this power is released in the form of heat, okay? Now, so what to do with the heat? All right, so this is to do with heat transfer. Now we know that heat can be transferred in 3 modes: conduction, convection, and radiation. For our case, we only need to look at the first 2. Okay, we only need to look at the first 2. All right, now when we look at the transistor, when you open up, right, this is how it looks like. Inside is a die, okay, a piece of silicon, and then of course they're connected to the 3 pin, okay. So it's attached on a piece of metal frame, okay, and of course there will be the wire bond, okay. They call wire bonding. They will connect into 3 pin. There's 1 die, okay, and a wire bond. Okay, now when we look at the transistor carefully, okay, we have heat sink, okay. This is the heat sink to help dissipate, okay, the heat. And we always have a thermal interface material. Okay, so this is usually the thermal gel. It's just like toothpaste, white color or a bit transparent that you can see they inject on the heatsink computer, right? You put it. The purpose of this is that it will help the heat transfer. okay, it will help the heat to transfer properly, because if you don't have it, there are always gap in between. Okay, and this gap, right, it will have, you know, even we see it cut so flat lah, microscopically, there is a lot of gap there. Okay, so the gel is to fill up all the gap. The conduction, yes, to increase the heat conduction. And then you will have the this metal piece at the back. This metal piece very important. And we have a die. Okay, now if you want to model this heat transfer, right, you can model it like that. It's just like electric circuit, but it's not resistor, it's not voltage and current. Okay, now you can see the point here. The junction of this, the heat originate from here, right? The die. Okay, so this is the heat. Heat is just like a current source. Okay, so it will go through this, the junction. And the junction here go through, okay, the interface, right? Okay, so it will go through this. It's just like another resistor. Okay, so the point, you see this is the surface of the case, and this is the heat sink of the mounting. Okay, and then lastly, this is the ambient air. Okay, the ambient air or the ambient temperature. All right, so this ambient air, and it have interface. That means this interface heat sink and the ambient. So this part is just like there is a resistor lah, the heat resistor. Okay, like this part. Okay, so we have interface to the case, right? So you just imagine the dot lah. It's just like have a resistor here. So this is how you model heat transfer. You look at like electric circuit, okay? And then you have to know all and all this resistance, right, is for the conduction mode, the heat transfer. Now, if these are all very high value, means that it's very poor conductor. The heat will accumulate there and until so high. If the thermal resistance, we call thermal resistance, it's very low, means like metal lah. The heat transfer very fast. So this is how we model. Same, even you go to this mechanical engineering, they will learn something like that. Okay. Okay. Now, this is just another diagram. If you say still cannot clear, you see this one. See, heat sink, air. Now remember, like this one is just like a heat transfer, a resistor. You see, a resistor. 3 resistor, right? 1, 2, 3. Thermal resistor 1, 2, 3, right? So in between the point here, and the point here. Okay, this is the air. Okay, and this point is a heat sink. And heat sink connect to the transistor case, the metal case. And in the case connected into the die, the junction. Okay, so this is another way of representing it. Okay, so now when we want to model transistor heat transfer, the data sheet also gave us this information. So that's meaning that when they produce this transistor, right, they already consider this is a very important information. So they call it thermal resistance. So it's not I bullshit, it's really thermal resistance. But this is not ohm. It's not like 10 ohm, 20 ohm. That was electrical resistance. So make this clear. Now in data sheet, they tell you, junction to case, 1.15 Celsius per watt. This is a unit. Okay, case to heat sink or case to flat. Okay, typical. Like I say, got typical, they get typical, no typical, they just eat yourself. Now, junction to ambient, 62. So they give you all this information, okay, for you to model okay, the heat transfer. It's important that because with this one, it will help you, okay, to actually understand or know how big your heat sink should be. If you keep on, okay, if you keep on like, don't do it properly, it will overheat and damage your transistor. So this one, MATLAB also can do it. So here is one example. All right. Okay. I show two first. Okay. Now you can model this one in Simulink, where you can get all these thermal resistor, okay, to connect. Remember they give you three, junction to case, case to heat sink to ambient. Okay. Then junction temperature, this is the source. Okay, and this is the power dissipation equation. And then, of course, we need to measure the temperature lah. All right, we can measure the temperature at this point, which is the case to heat sink and heat sink to ambient. And your ambient temperature, you can actually set. Now, ambient temperature is very important because like our ambient temperature now, most likely like 20 to 25 lah, right? So that's why if you know the ambient temperature is, let's say 16, then you don't need that big size of heat sink because the ambient temperature is cold. But if you know that your ambient temperature is 30 degrees, then your heat sink needs to be bigger size. So that will help you to determine. All right. Now with all these three, what we call this thermal resistor, okay, then you can key in this value. Okay, then with that, right, you can actually model, okay, this what we call this the junction, okay, temperature and so forth. When you run the Simulink, right, so you can actually see that, okay, the temperature at the back of your, what we call this transistor, okay, the case to heat sink, this part, it will shoot up to 83.4 degrees. Okay, it will shoot up to that high. Of course, you can change, okay, this one, the heat sink. If you change the heat sink, then you will see it will actually, okay, will, like for example, it will just reduce it. How much is reduced? Okay. Maybe we try this one first. Okay, we try this one first. This one, I think we don't have time to model this for today. We try this one because this one no need Simulink. I already written a code. You can run this immediately. So we'll do this in the next class for this modeling. Because I have a few modeling for you all to do lah. Okay, as for today, again, please download this. Okay, so this is the thermal demo. Also based on IRF 540. Okay. So I think this one will show clearer, right? Now, the die, okay, the die here, the junction to case is 1.15 based on data sheet. And the metal at the back here, case to heat sink, right, is 0.5. And lastly, the heat sink itself. Okay, the heat sink 60.35. And then our ambient temperature is 25 degree. Okay, and the power dissipation, okay, is 0.97 like I showed just now. Now, let's say if you change this power dissipation to, let's say, 1 watt, okay. Now you can see that I changed to 1 watt, what happened? My heat source, okay, and the case to heat sink temperature will go up to 85.4 degree. Now, if I keep on increasing the power dissipation, you see the temperature can go up to 145. That's why the data sheet sometimes show you up to 150. It's not joke, you know, it's really, it can go that high. It really can go that high. If your power dissipation is 2 watt, you can see the heat source. That means it go past through all this, it will get here. Then of course, if you reduce the ambient temperature to, let's say, 15, it help a bit lah. You see? Now it reduced 10 degree. Okay, it reduced 10 degree. Now, if you increase this one, 16.65, this is your heat sink. Okay, this is your heat sink thermal resistance. A bigger heat sink means what? Higher conduction, right? Okay, so I increase the heat sink. Sorry, not higher conduction, it's lower because the key Kelvin per watt. Okay, now I lower it down. Okay, lower the thermal resistance. So sorry, I got it terbalik already. I lower the thermal resistance. Okay, so it becomes bigger heat sink. So you can reduce, okay, the temperature. Now let's say I further lower to, let's say, 20. Now you can see that even the power dissipation is 2 watt, but you design a heat sink with a lower thermal resistance, and you put it at a place where, you know, you bring it up to Genting Highland, 15 degree. So your power converter, no issue. Okay. This is how you work on it. So you can play around, so you can know that, okay, what if your ambient temperature increase to 20, then you will see it will affect all this. Now these two cannot change. 0.5, this one is a transistor, came from the data sheet. You cannot change. Okay. But what you can change is the environment temperature and the heat sink. Okay. So this is heat transfer. From switching losses lead to heat, and then what types of heat sink you need to use. This is also another very common problem UCSI student always did. You know, assignment, right? You all test never put heat sink one. Because you're on for a while, you're off, no problem, right? Again, you are killing the transistor slowly. So during test, no issue. The moment you come and demo again, sir, yesterday, no, this morning still work. But I don't know why. Of course, you slowly every time overheat. It's so coincidentally, the moment you come to the final presentation, it doesn't work anymore. Okay, but if you take this into consideration, this will not happen. Okay. All right. Next class, we will go through this, or we straight away go through this. Now, after you know this, right, you can actually model your electrical and thermal at the same time. Okay, something like that. Your transistor here in MATLAB, you can actually, like, okay, if I put a heat sink, what will be my temperature? All right. Now for heat sink, right, how do I know the thermal resistance of a given heat sink? Okay, like for example, I got this heat sink. Okay, then of course, I just put a website. I hope this website is still around. Sometimes element 14, you know, they just change the product to somewhere else, then say product cannot find. Okay. Okay, got. Okay, now you will see when a lot of people, right, they go and, okay, for example, a lot of students, right, when I ask them to buy his thing, I ask them very simple question, why you choose this? Oh, leng chai cheap lo. Voila, paying sun, you know. Of course, those who really listen to my class, they will tell me, say, sir, I chose this because it have a thermal resistance of 24. See, written here. So that means if you are not sure, you know, hey, can tahan or not? Okay. Let's say I put back to 1 because this is too high already. I put back to 1. Okay. And then okay, now you want to do this, right? Okay, our room temperature is 25. Room temperature is 25, voltage dissipation. And when you turn on the transistor will go up to like 45 degrees, which is warm, right? This is the normal you all feel. And then you are not sure, okay, is this heat sink good or not? You just put here and see. Okay, now, okay, this heat sink is 24. Okay, so it will give you around 49. So obviously not so good, right? Let's say you want to bring it down. Then you can see the heat sink, the size you can see, the transistor is here. And this one, you see, this one obviously better, right? So big. And then, okay, you see the thermal resistance is 6.8. So from here you can say, okay, if I put 6.8, if I buy this one, okay, you see the temperature go all the way down to 31. No issue for your problem already. So, yeah. When you go Jalan Pasar and buy his thing, ask the guy, what is the thermal resistance? But I know majority will look at the leng chai or not, first thing. And then cheap or not. Of course, you look at the price, you know lah, this one 12 ringgit. But then this one is only 1 ringgit. Of course, save money ma. And usually it will still work during demo lah. And then it left in the lab after a few times, then cannot work anymore. Like I say, it really depends on your design. Okay, I don't say this is bad. For some design, right, if the power dissipation is less than 1 watt, I mean, it's still acceptable. And this one, you can see, like for example, okay, it really depends on the fin design lah. Okay, like this one, okay, also like around 24.4. Okay, not much different, 35.9. Okay, this one does fit the transistor one, really not much difference. But at least it gave you an idea, you know, of the importance of the heat sink, because these two already given. Okay, then you can see, oh, if I use the cheap one, 24. Okay lah, 49, I think it's still okay lah. Because remember, the data sheet state that the transistor can withstand up to 150 lah. If you think it's okay lah, if you know, I mean, doesn't mean that you must put it very low. But when you come to a very complicated design, okay, this really play a very important part, especially again those mechatronics students who like to control motor, robot, move like that, and then suddenly stop, cannot move anymore. Because they don't have heat sink. Okay. All right. So this will give you some idea lah, at least on the thermal modeling. Okay. Of course, this is a program that written by myself. Not much you can change, but next class I will show you how to do that in the in MATLAB, right? The Simulink, how to connect them. Because this one is fixed, you cannot model other thing. You only can model transistor. But it's good enough already lah. This one, even for super lazy student, don't want to do the model lah. Do that also can. So, like I say, ambient temperature play a very important role. Okay, so that's why the data center, you know, inside no people, you go in lah, oh shit, like Genting, 16 degree, so cold. It's cooling the server. Okay, it's cooling the server because they control the environment. Like this case, I put this thing into a data, what we call even a small heat sink, right? You can see the temperature go down to 40. So it up to you lah, how you want to prioritize the design. It's just not to overlook all these important factors. You see, in the past, electronic, your transistor is either on and off. That's all. Okay, base, collector, emitter. That's it. End of story. Happy. You think you know everything about electronic already? No. So in power electronic, I bring you further to show that okay, transistor not just simply on off. They have important characteristic that you need to understand it from data sheet. Okay, and then at the same time, the switching frequency, okay, does affect the power losses, and these power losses, all the while we just think power loss lah, but it convert into heat. So I move further again, how to deal with this heat. I believe in the fight you all don't care. You know that there's a problem, but I don't care. So now, and then I move you another step further is that all the time you look at the heat sink, but you have no idea what this heat sink is about, right? It actually gives you a thermal resistance. Ask the shop, or if you know how to read the data sheet, read the thermal resistance. Get the transistor you want to use. Model it in MATLAB. Make sure that the transistor didn't shoot up until so hot, right? Until you burn your hand or whatever. Okay. So I think, yeah, almost time already, I know. All right. So any question for today?
So I have a question regarding the temperature.
Yes.
So what is actually the optimum temperature for the transistor?
The transistor, I don't say the we don't use optimum, the acceptable temperature range. Okay, it's around 50.
Okay.
Now you see 50, when we use our hand to touch, right, it's actually warm, not like burning. And you will notice that all the computer chip, they're set at 80 degree. Okay, at 80 degree, it will just shut down your computer, reboot your computer already. For our handphone, right, they go up because handphone, they cannot put a very big heat sink, right? The heat sink is there, but you know the thermal resistance is low. So if you use I mean you can feel it out when you play what Wangzhe or what type of game you all play until you feel hot on your hand.
Wangzhe.
Yeah, Wangzhe, right? Okay, because it's CPU intensive. So that is the temperature you feel. It's around like 40 to 50 that range. So that is the acceptable range I would say. When you all see the people test, wow, Wangzhe, wow, 50, wow, good. 80 is the dangerous. Okay, that's why all CPU shut down at 80. They're designed to be shut down at 75 to 80. Those can go up to 101, usually is for space or undersea application. Space is vacuum, temperature -0, no problem. The ambient is so low already. It still generate heat. Okay, I mean, you can try my MATLAB code, right? If I put this to space, it's 0, let's say, not say space, let's say you put the Antarctica, you see, it go down to 24. Normal room temperature. You bring this to Antarctica or, Okay. So I hope this class today is useful to all of you. Let you all know more about transistor, which electrical engineer will encounter very often. All right. All right. Any questions? Okay. So if no question, then we will end the class today.